Okay, so this chapter is going to be an informal introduction to principal component analysis, PCA. So let's recap. Let's suppose we are given n data points, x1 to xn, each of which is a vector of length p, and we're going to stack these into a matrix X, where x1, the first data point, is row 1, down to the nth row, which is going to be xn transposed. So this is an n by p matrix. And for this section, I'm going to assume that x has been column centered. So in other words, the mean of each column is 0. If it hasn't been column centered, replace x by h of x, where h is a centering matrix. Okay, or equivalently, replace x by x1 transposed minus x bar transposed down to xn transposed minus x bar transposed. So subtract the mean from each row. So the covariance matrix S, sample covariance matrix, is 1 over n sum of xi transposed minus x bar transposed, but we're assuming we've been column centered here, so let's assume that's 0. Okay, so this is just this term here, and if you stare at this for a few moments, you'll realize that this is the same as x transposed x. So let's just say then that given some vector u in Rp, we're going to let the yi be our transformed variable. So that's going to be u transposed x I. Okay, so that's going to be our first transformed variable. So just a few things to notice about our transformed variables. The first is that y bar is the sum of yi 1 over n. Well, that is just 1 over n, the sum of u transposed xi, which is u transposed sum of xi over n, but we said the data have been column centered, so this is just u transposed 0, so it's 0. So the sample mean of our transform variables is 0. The variance of our yi's is going to be u transposed s u, okay, where s is the sample covariance matrix of the x's. So to see this, note that the variance of the yi's is 1 over n sum of the yi squared, and because they have sample mean 0, so I don't need to subtract the mean squared. Okay. Well, this is just 1 over n, the sum over I here, of u transposed x times, u transposed xi times squared. Okay. Well, let's just rewrite that. U transposed x is the same as x transposed u, so this is the sum over I of u transposed xi times xi transposed u. Well, this is 1 over n u transposed, the sum of xi transposed u. So what's that equal to? Well, 1 over n, the sum of the xi transposed, is just s, so this is indeed u transposed s u. So this is for any choice of vector u here. If our data are column-centered, okay, if we compute our transformed variables, yi, which is u transpose to xi, then the transformed variables have mean 0, and they have variance given by u transposed su. So we said in the previous video that PCA aims to maximize the variance of the transformed variables. So it's going to maximize the variance of the y's. So that is seeking to maximize u transposed su. Now the first thing to note here is that if the vector u is completely unconstrained, this problem doesn't make sense. Okay, if u transposed su for some choice of u equals 10, say, then if we let u be 10 times u prime be 10 times u, then u prime su prime will be 10 squared times 10, so it's going to be 1,000. Okay, so we could make the variance arbitrarily large by just keep scaling u. Okay, so the question doesn't make sense as written. So what we do instead is we seek to solve the constrained optimization problem, and we seek to find u to solve the problem that maximizes u transposed su subject to the length of u being 1. Okay, so the length of u, of course, so we using Euclidean inner product here, this is just u transposed u square rooted. Okay, so principal components analysis tries to maximize the variance of our first transformed variable yi. In other words, it tries to find the u to maximize u transposed su. And in order to make this make sense, we have to pick a u of length 1. Okay, so just trying to find a direction in the data that is most variable. So what's the solution to this? Well, we know the solution already. Okay, we know from the proposition we saw in the previous chapter that the maximum to this is achieved at the first eigenvector. So the maximum is achieved at v1, so which is the eigenvector of S with eigenvalue lambda 1, the largest eigenvalue. Okay, and in that case, the maximum will be u transpose. The maximum of u transposed su will be v1 transposed s v1. Okay, well, s times v1. If v1 is an eigenvector, it's going to be lambda 1. So it's going to be it's going to be lambda 1 times v1. So that is going to be v1 transpose times lambda 1 v1. So it's just going to be lambda 1 v1 transposed v1. Now these are unit eigenvectors, so this is just lambda 1. So the work we did in the previous chapter, proving these kind of seemingly obscure results, has paid off instantly. We know that the optimal transformed variable is y, which is v1 transposed x. Okay, if we apply this to each vector, we're going to get yi, let's put a 1 there to indicate the first transformed variable. It's going to be v1 transposed xi. So in general, we shouldn't work with eigen decompositions, with spectral decompositions. We should work instead with the singular value decomposition, as it's more numerically stable. Okay? So rather than working out the eigenvectors of S, the covariance matrix, we're going to note that S is 1 over n X transposed X. And so the eigenvalues of S are the square of the singular values of X over root n squared. Okay, so in other words, the square root of lambda 1 is the first singular value of the matrix 1 over root n x. And in practice, that's going to be a much better way of doing PCA. It's going to be done by the singular value decomposition. And so just a word on the scaling of the eigenvalues. We know that if you multiply the matrix X by some constant, that just multiplies the singular values of X by the same constant. Okay? So if sigma I is the ith singular value of a matrix, okay, this ith singular value of the matrix C times X is C times the ith singular value of X. So in particular, sigma I of 1 over root n x is just 1 over root n sigma I x. So that's just a useful fact that we're going to need to remember when we code up PCA ourselves. So now we want to consider the second principal component and later principal components. So we know that y1 has maximum variance. What should we choose to be our next variable? Okay, so we're gonna let y2 be of the form u2 transposed x. Okay, y1, remember, was v1, the eigenvalue of s, times x. Okay, so what vector should we choose for the second component? So how should we choose u2? So we're going to do the same thing. So we're going to choose u2 to maximize the variance of y2, okay, subject to y2 being uncorrelated with y1. Okay. So why uncorrelated? Well, we don't want to count the same information twice. Okay, so it makes sense to pick an orthogonal variable, the variable that is unrelated to the first transform variable. We don't want to capture the same information multiple times. So what does that uncorrelated condition look like? Well, first of all, let's compute it. Okay. So the covariance between y1 and u2 transposed x. Okay, so we're considering the covariance because if the covariance is 0, then the correlation is automatically 0. So we just need to find something that makes the covariance 0. Well, the covariance between these things is going to be 1 over n, the sum of, let's write this in, we're going to have u2 transposed xi times xi transposed vi. Okay, using the same trick as we used before. Well, this, you're going to see very simply, is just u2 transposed 1 over n sum xi transposed times vi. So this is u2 transposed s v1. Sorry, I made a typo here, didn't I? So these shouldn't be VIs, these should have been V1s, my apologies. Okay. Yeah, that V is fixed. Okay, there's no I there, it's the first eigenvector of S. Now, we know that V1 is an eigenvector of S. So this is just going to be lambda 1 times u2 transposed V1. As S V1 is lambda V1. So, to make the correlation 0, we need u2 to be orthogonal to V1. Okay, so we need to find a vector u2 that is orthogonal to the first vector we picked, v1. So our eigenvalue problem is going to be maximize u transposed SU subject to, well, we still need u to be of length 1, but in addition, we're going to require that u transposed v1 is 0. Now we're going to prove this in the next section, but the maximum here is achieved at u equals to the second eigenvalue. Okay, so we're going to prove this later, but it's probably not a surprise that the answer here is going to be take the second eigenvector of S. So the eigenvector of S corresponding to the second largest eigenvector, lambda 2. In that case, the maximum of u transposed SU is going to be lambda 2. So our first variable then, y1, is v1 transposed x. Our second variable, y2, is v2 transposed x. It's not going to be a surprise that the rth transformed variable here is going to be VR transposed x, okay, where VR is the R eigenvalue. So we're going to prove this in the next section, okay, but just a comment on terminology here. These two, the transformed variables, are commonly referred to as the principal component scores. So these are the principal component scores, they are transformed variables. The eigenvectors, v1 up to vr, whether we stop computing, okay, are called the loadings, or sometimes simply the principal components of the data. Okay, but terminology does vary here, so just be careful. Okay, so the transformed variables are the principal component scores, and the eigenvectors are the loadings or principal components. So just a quick word on the geometric interpretation then. So let's suppose our points lie in Rp. Okay. We can think of the subspace V being the span of some of the eigenvectors. So let's have V1 up to VR. Okay. So this is a subspace of Rp. Okay. So where the Vi here are the eigenvectors of S, or if you like, the right singular values, the right singular vectors, sorry, of X. So PCA aims to project X onto V. So it's going to project all our data onto this subspace V. Now we saw that the projection matrix for doing this in chapter 2. We saw that the projection matrix for doing this was if we let the vector V be the vector with columns given by the eigenvectors, so V1 up to VR. Okay, so this is a P by R matrix. We've seen that the matrix for doing this is V transpose V inverse V transposed, but we know that I transposed V J is 1 if I equals J and 0 otherwise. So in other words, V transposed V is just the identity matrix. So we have that PV works out to be V transposed. Okay, so that's our projection matrix for projecting the data onto the subspace V. So the coordinates of the data projected onto V with respect to the basis V1 to VR is just Y, which is V transposed X. Okay. So we project each data point X, and we get the coordinates of that projection with respect to the basis vectors V1 to VR. It's just V transposed X. And we can do this for each data point. So, yi is going to be V transposed xi. Now, if we stack all these y variables into a matrix, so if we let capital Y be the data matrix of the transformed variables, so we've got the first transformed data point y1, okay, down to the nth transformed data point yn. So this is an n by r matrix. Well, if you think about that, yi transposed is going to be xi transposed v. So after a few moments of thought, you'll see that this is xv. Now, if the singular value decomposition for x is u sigma v transpose, that might be a truncated singular value decomposition. Okay. So the SVD for x, you'll quickly see that x times v, well, this is u sigma v transpose v. V transpose v, we know it's identity, so this is just u times sigma. So y is u sigma here. So this is our n by r matrix of transformed variables.